Hello, my name's Christoph Fürst from RIEGL Laser Measurement Systems, and today I'm here to talk about one of our newest innovations in the terms of terrestrial scanning, the RIEGL VZ400i. First off, I'd like to start with a very brief introduction of our company. We are a small, privately owned company, founded and still operated by Dr. Johannes RIEGL. We're located in Austria, to be more precise, around 80 kilometers northwards from Vienna, in a small town called Horn. We're active in the production of scanners for terrestrial applications, airborne, mobile, recently more and more growing the unmanned sector, as well as the industrial sector, thus being one of the only companies producing scanning devices for all of these fields, with a total portfolio of currently around 30 scanners. So far for the company itself, I want to first start off with what was there before we got to the actual VZ400i, so what's its heritage. Afterwards I'm going to continue with what did we actually improve, what did we add on, what makes it actually special. I want to give an overview on what happened in terms of firmware and software, and finally I also want to show what can be achieved with the scanner itself. Now, how did it start? In 2008 we first introduced the VZ400, the first scanner that we had, terrestrial scanner that we had, which offered online waveform processing, echo digitization, and also it had its own inclination sensors. I'm going to explain most of the terms that I use at a later point. So it was a huge step forward. Finally, you didn't always have to be 100% precise about the leveling of your scanners, and you could just set it up. Following that, we introduced the VZ1000, which brought in further range, making it also applicable in bigger mining sets and different locations. One of our more recent introductions was the VZ2000, which came with 1 megahertz measurement rate. So that was a huge step forward in terms of measurement velocity, along with 240 lines per second of scan speed in order to actually efficiently use that high measurement rate. Afterwards, we have here the VZ4000. It's a very long measurement range scanner. It ranges up to 4 kilometers, which makes it perfect for either big mining sites or very big topographical surveys. And up to this point, all of the scanners are eye safe. Last but not least, we have in our VZ line the VZ6000, ranging up to 6 kilometers. It is not eye safe anymore, but laser class 3B. That is because it uses a wavelength which makes it very suitable to work in snowy and icy terrain, for example, for glacier mapping. Now, while we always, three of these scanners we have also integrated into our own mobile solution, namely the VZ400, 1000 and 2000. And here again, the VZ2000 was brilliant because due to its higher line speed and measurement rate, it enabled you to drive twice as fast as with the other scanners. But still, it is the best possible upgrade you could get if you already own a VZ scanner. Instead of taking the scanner position by position and taking scan for scan, with a scan pattern, of course, being wider and wider the further you get, you could now take with a single resolution, having the scanner either rotating around for a quick overview or having it facing straight into one direction for more detailed acquisitions. So the VMZ basically is the next step if you want to go from TLS to mobile. And even though we recently released new products and constantly do so, the VZ400 still maintains one of the fastest scanners on the market, because we constantly add new improvements, starting with an add-on battery in order to make it more mobile, in order to make it easier to transport around, along with the 2011 introduced full waveform output, which we took from our airborne scanning units. The full waveform output enables you to directly access the waveform that you get from the scanner, and therefore be able to write algorithms yourself in order to classify them into first, second and further targets. Which now finally leads me to the actual RIEGL VZ400i. Now, what makes it different? It's of course faster and has a higher line speed, but what is the main difference is that it can actually take post-processing tasks. So it can register your data after you acquired it, it will filter it, and it can also georeference it. following by the possibility to upload the data. We will integrate an LTE modem on top so you can connect to 4G and 3G networks in order to upload the data while you're still on site. Furthermore, the scanner has an increased range of up to 800 meters, whereas its predecessor ranged up to 6 meters. Its measurement range, its pulse repetition rate by now is at 1.2 megahertz, leaving you with a measurement rate of 500,000 points per second. Just imagine that makes it possible with a line speed and frame speed in 2.5 seconds to acquire an all-around scan holding 1.25 million points. So in 2.5 seconds you have a quick overview of your whole situation. Also, the scanner will be able to resolve range ambiguities using multiple time-around processing in real time. Now, what does that mean? As already mentioned, we have the direct comparison of just the stats, but just to see, we now take 45 seconds for a scan of 100 times 360 degrees, so that's the whole field of view, with a resolution of 7 centimeters at 100 meters or 7 millimeters at 10 meters. That's 22.5 million points in 45 seconds, whereas previous scanners with only 300 kilohertz still needed 3 minutes. So that's 4 times faster. Also, we introduced a new graphical user interface. In order to make it more accessible and more intuitive, we put in a high-resolution touchscreen and changed the whole design, so it's now a lot more intuitive. People should be able to grasp it, because it's not like there's always the one person who has been taught how to use the scanner by us who uses it, but companies expand, new people come, and then there's second-hand teaching, stuff gets left out, and a new intuitive design allows people to find out stuff for themselves. Also, the scanner will be able to run third-party applications developed by our customers. Furthermore, we accelerated all of our interfaces. So instead of having 54 megabyte per second for the Wi-Fi, we're now up at 145 megabyte per second. The gigabit connection went up from a 100 megabyte connection to, like I said, a gigabit connection, so 10 times faster. And all the same, we increased our additional storage port as well as the camera port from USB 2 to USB 3, again making it around 10 times faster. So that means while we didn't only focus on the acquisition as such, we also focused on the data transfer, because time at some point will remain the only factor that decides whether a scanner is feasible and accessible or not. Next off, we have an internal storage of 256 gigabyte SSD as the basic set, also optionally to be delivered at 512 gigabit if people want to do really big projects. With the scanner being faster and being able to handle more data, it's of course very inviting to just take more positions and take them with a higher resolution, because the time is not an issue in this case. And thus, of course, more and more data sums up. So even if you fill up that full hard drive, you have first off the previously mentioned USB port and also an additional SDX card slot, again ranging up to 512 gigabyte. We have a gigabit connection on top, so you can connect to vision cameras just like the FLIR camera in order to have a thermally colorized scan. If you want to know if there's any flaws with any kind of insulation, that's quite handy. Also, we brought in Bluetooth 3.0 for remote controlling and also the connectability to modern GNSS receivers, as well as we will integrate an LTE modem, which will enable the scanner to directly connect to mobile networks in order to upload your data from wherever you are, of course, if you have the connectivity. Next off, it will be able to fully georeference itself. So we have, first off, the integrated L1 GNSS receiver, which receives GPS, QZSS, GLONASS, and Baidu, and yes, all of that simultaneously. We have an MEMS IMU, which gives you roll, pitch, and yaw, and it gives you these orientation values at any kind of position. So you don't have to worry, are you within a certain angular spec, but you can also turn the scanner upside down and you still get your angular orientation. And next off, a seemingly trivial matter, we discovered that some tripods come with a way longer thread than others, and this could lead to some of the scanners not being mounted securely. So we fixed this issue by implementing a longer thread. And now for a direct comparison. So previously, what was already there in the previous scanners, we had the VZ400i LiDAR engine firmware. So this is more or less the same as with the VZ400. We upped the performance, but its main tasks are the echo digitization, which basically means sampling and converting the analog signal that we receive from the pulse we send out into digital form. The online waveform processing, which is taking the information and adding it to our data files from that digitized waveform. And then we have, of course, the compression into a small file so they can save it and later on extract it, and the housekeeping data. So it stores information like voltage and laser power. Now what is new is that we also put in a whole computer. We have now the VZ400i LiDAR system software. Now what that does is, of course, due to the interface, it controls the LiDAR scanning engine itself. But also it acquires and stores the information of the images that you can take with your camera, the GNSS data, and also the positional information that you get from your IMU. Also, it handles the previously mentioned post-processing tasks. The software is what will do the registration and what will do the filtering and georeferencing. Now, as I've talked about online waveform processing, I will quickly go through the attributes that we assigned to our data. First off, we have our pulse shape deviation. Now, if we have here a tree, and if we take a look here, we can see that there's a lot of edgy looking, like straight noise, which has assigned a certain deviation value. And once we select parts over a certain threshold, we can see that it will be selected and leaves us with a very clear point. So it's good for edge detection. We now have the tree here. I'm sorry, this is not the HDMI resolution, but you can really see the branches and twigs in their proper shapes. Again, the scanner has a multiple target capacity, meaning that if your footprint isn't fully covered, the rest of the footprint moves on and can select further targets. We now have here a mine site covered with fine meshes for protection of slides. And if we have a look here, we have it here in reflectance value, seeing that they're quite low reflective. And once we move on and take a look at the cross section, you can now see here that we have in yellow the meshes being first targets, as in something followed. We have the blue ones, so that there's data underneath the meshes, nothing's lost. And where the meshes directly applied towards the edge, we have single targets, so everything was selected. And here we have everything in between. So online waveform processing doesn't differ between second, third, fourth target, but it just classifies them at other targets. This is where the previously mentioned full waveform data output can come in, so that people can themselves access the waveform and write their own algorithms. We assign a calibrated amplitude, which is the ratio basically of what we send out to what we get back, and it is range dependent. Due to that, we also brought in the reflectance, which is the ratio of the actual amplitude of a target in comparison towards the amplitude of a white flat target at the same range. Due to that, we have managed to create a more range independent value. Now for a practical example, if we have a look here, we have here an urban setting, now amplitude colored, and as you can see, especially on the cobblestones, the further you get back, the lower the amplitude gets. Now if we move to the reflectance coloring, you can see that the distance now doesn't really make any difference anymore. If you have a look at the house on the left side, you can see that it's still a bit depending on the angle of incidence, but basically we have managed to get a range independent value for indication. And if you have a look at the traffic signs, they're highly reflective, so it can be very useful in order to quickly select them. Now to give a more detailed impression of the scanner itself. So what you see here is the LiDAR engine. As previously mentioned, it does the echo digitization and the waveform processing, of course also the acquisition. On top of that, we have interfaces. Now why is there 4 cameras? There is 2 antennas. There's 2 antennas for the Wi-Fi, and 2 antennas for the possible network connection. We have then an add-on camera of up to 37 megapixels, and we have our GNSS receiver, which can also be any kind of external receiver. So you can work in your own user coordinate system and at a higher positional accuracy. And inside we have the post sensors, which give us roll, pitch, yaw, and compass orientation, and of course the post processor. Now, while the LiDAR engine is handled by the firmware processor, all the other information is fed into the post processor, which will then handle the real-time data post processing and any kind of data conversion or registration. I've previously mentioned that the scanner will be able to do real-time MTA processing. Now, what is MTA? MTA means multiple time around, and once the scanner reaches a certain combination of measurement range and measurement rate, it is possible that there is more than one pulse at the same time in the air. This leading to certain range ambiguities because they're all assigned to the same pulse. And this leads to this red, flat, mist-looking like data. Now with ReMTA TLS, our software to resolve this, the data will be moved into the proper section. And as you can see, we have here still more usable data in further distances that we acquired at our high measurement rate. Next off, the scanner creates an RDB SDK. So this SDK now is version 2, just like is used with the recently released RISC Pro version, and as will be introduced in our mobile and airborne software reprocess. Now what that means is, this is a database that enables visualization of very large point clouds. I'm talking about hundreds of millions of points that can be easily visualized and moved around and worked with. Once it has this database, it comes to the step of registration. Here it can use any kind of information that we previously fed in, whether it's the GNSS information or any kind of reflectors that we have set up previously and fine scanned. It can also, of course, combine these both. But sometimes projects need to be faster, and if there's no necessity to set up reflectors, you can save the time by working with the overlapping areas of your scans. Therefore, we have our adjustment module. It's called Multistation Adjustment, and it's an ICP algorithm that detects surface normals and try to use them to fit the scans properly together. If you have a look at the right, you have the scans before and afterwards. So it directly uses the geometry of your actual project. And once that is done, we have Geosys Manager, which enables you to accurately georeference your data. So it has access to the EPSG database, meaning that you can download your coordinate systems, you can customize definitions, and you can of course export and import coordinates. Now for last, to give a better impression of what the scanner actually does, I have here a project taken a few weeks ago in Fraunhofen. Fraunhofen is a small town next to Horn. The project consists of 32 scan positions, each of which took 1 minute and 45 to take. The positions are taken at the resolution of 40 millidegrees. Just to get that a bit more clear, it means up to 22.5 million points per position. It's a total of 452 million points, and the total acquisition time, and by acquisition time I'm not talking about actual time measuring, I'm talking about taking the scanner, putting it to the car, driving there, taking the project and going back, is 2 hours and 50 minutes. Each position previously measured the orientation and GPS data, and also included scanning and the taking of images. So I hope that gives you a nice imagination of how the scanner can really be used to quickly acquire basically what is a small town. And while the project, I will still leave the animation running, it's a bit longer, but just so you see where it finally leads up to. Okay, I will now just skip, and basically what you get out of it is, for example, here for better visualization, I deleted grid and any kind of other additional inputs. But what you can get out of it is a digitized 2D or 3D plot that you can freely measure in, and that is all in around 3 hours of total time, including, of course, processing and everything, preparation. So thank you for your attention, and if there are any questions, of course, now I'm here, and I'm here all of the days, so feel free to ask anytime.